In this screencast, I'm going to demonstrate using an Excel spreadsheet to determine kinetic parameters. We're using nonlinear regression, and we're solving numerically the ordinary differential equation for mass balance for a plug flow reactor. And in previous screencasts, described the equations being used and showed the setup of the spreadsheet, but in order to keep these screencasts a reasonable length, we've broken them into several parts. Here I'm going to look at the actual spreadsheet and some of the terms. So let me pause and bring up the spreadsheet. So we're looking at the spreadsheet, and a couple things to point out. If I select the cell for Ka, and we look in the upper left hand corner, we see we've named that cell Ka, and we've named the cell below it K. Much easier in our calculations if we name the cells. So likewise over here, name pressure and temperature and so forth. So the Runge-Kutta terms, I explain how we get those terms. If we look at one cell, we can see the calculation where we're using the volumetric flow rate, V0, and we have the K terms, and then we're using the concentration. So I11 is the concentration here. That's the inlet concentration in the reactor. We're always using concentration from the previous step in the next calculation. So if we go down to here to calculate K1, we're using I12, which is the concentration we calculated in the previous step. So we step through. There's 400 steps to get to a volume of 20 cubic centimeters. Now, the valuable part is over here with a table. So what I've done is first type in the values where the measurements were made for volumetric flow rate and the experimental values. So these were generated using the computer, but they are generated and noise added. So these are experimental values for these flow rates. And then the critical thing is now in this column, you'll notice if you look up here, it says table D8. So what that means is D8 is the volumetric flow rate here. We're going to change the volumetric flow rate because what I've done is I typed in this volumetric flow rate, and then to create a table, I had to select these values. So let me step back and show you. So before these values are calculated, I select all of these cells, and the important thing is here, this is equal to, if we look up, it's equal to I411. That's the outlet concentration from the reactor. When we finish that numerical integration, it's the last value in this I column, X of the reactor. The way the cell works, this cell here determines what values we're going to substitute in here. So when I select this and then I go to data and I go to what if analysis and I go to data table, in this case, all I have is a column input cell. And so what I would do is select these values. And if I hit return, I don't want to actually change the cell. Then we would, and then I would hit OK, I'm sorry. Then it would actually change. So let's not actually do that. But the way the table works, it uses this value for the calculation, and it calculates this particular cell, I411, here for a flow rate of 1, here for a flow rate of 2.4. And so if I were to change K up here, let me just change this to say 0.2. It's going to actually do that numerical integration for each of these volumetric flow rates and then put the values in the table. So since I don't want to make that change permanent, I'm going to go back to where we were. So over here now, the fact that we've generated what we expect the concentration to be leaving the reactor for the reactant for whatever K values we put in here. And of course, when we start, we put some values that hopefully are reasonable, and we're going to iterate to them. And so we want to compare these calculated values from the ordinary differential equation solution to our experimental values. We take the difference. So if you look at this cell, it's the difference squared. And we sum up those values. This is what we're minimizing. So then what we would do is go to Data, Solver, and I've already selected it to minimize all the variables non-negative. This is the cell with the sum of the squares. These are the cells for K and K. If I hit solve, it'll go through and solve again, and it'll then generate the best values, which of course then changes these values, assuming I started with some numbers other than the answer. And then I can also calculate the residuals. Here is just a difference between the experimental and the calculated. If you look at cell up here, it is residual squared residuals. And so then what I can do, and I have some notations explained in the spreadsheet, I can make a plot, just insert a plot, so I won't go through how to do that. I'm assuming that that's something everyone is aware of. I can make these plots to better characterize how well our fit is and if it's a random distribution. So the spreadsheet, which is available on the LearnChemE.com website, also has the formulas so you can look and see exactly what formulas used to calculate the K values at each step. And then it shows the data table. Now it also shows how we go about doing the confidence limits, but that takes some time, so I'm going to do that in another screencast.